This video is over the rational root theorem. The rational root theorem basically gives you the guidelines in order to find your rational zeros. And remember, a zero is where the polynomial hits the x-axis, and you might also hear those called solutions or x-intercepts. And this basically says that when you set your equation equal to 0, every possible rational zero is going to be in the form of p over q. P are the factors of the constant in the equation, and Q are the factors of the leading coefficient. And the leading coefficient is the number that's in front of your highest degree. So it's very important that you know which two numbers you're going to be working with. All the other numbers in your polynomial don't really matter. Those aren't going to be helpful in terms of actually deciding what your possible zeros are. And the reason this theorem is so important is that it can help you identify or at least narrow down where your graph is going to hit the x-axis. In this first example, we're going to be going through and listing all the possible rational zeros, and then in example 2, we're going to show you how to actually find those zeros. In this example, I've got f of x equals 4x to the 5th plus x to the 4th minus 2x cubed plus 8x plus 5. And what we're going to do is identify the factors of p and the factors of q, and then write them all as fractions. Remember, our theorem says that p are all the factors of your constant term, and the constant in this case is 5. So I'm going to list all of my factors of 5. That's going to be 1 and 5. And then the q value is all your factors of your leading coefficient, and that's going to be 4. So all my factors of 4 would be 1, 2, and 4. So once you have these listed, all you're going to do is write them in fraction form, and it's always p over q. So I'm going to take each p value and divide them by the numbers I have listed in q. So I'm going to take 1 over 1, which is 1. I'm going to take 1 over 2, which is 1/2. 1 over 4, which is 1/4. 5 over 1, which is 5. 5 over 2, which is 5/2. And then lastly, 5 over 4, which is 5/4. So notice I do every combination of all the p's over all of the q's and write them out this way. And then each term that you have listed here is going to have a plus or minus in it, because you can hit at the positive value or the negative value. Now, it looks like I have a lot of possible zeros listed, but remember, you only can have as many zeros as your highest degree. So my degree in this case was a 5, which means total I'm going to have 5 possible zeros. And it may be all 5 from this list, or you might have some that are imaginary numbers. And that's where Descartes' rule from the last video can come in handy, because if you know how many positives, negatives, and imaginary numbers to look for, you'll have an idea of which numbers or how many numbers you need to test. So if you have any extra questions on how to list the potential zeros, let me know. But now we're going to be talking about how to actually find those zeros. To actually find the zeros of your polynomial, there's going to be 3 steps I'm going to want you to follow. The first step is going to be to list your possible zeros, just like we did in example 1. So I've got an equation here in example 2, and it says find all the zeros of this f of x equation. Notice that our degree is 4. That means we're going to eventually be looking for 4 zeros, and our leading coefficient is 3 and our constant is 5. So this is our p and this is our q. And so I'm going to go ahead and list those possible zeros. So we'll start with p. Our possible factors of 5 are 1 and 5, and our factors of q are 1 and 3. And remember, it's always the p's over the q's, so I'm going to go ahead and list those possible factors. 1 over 1 is 1. 1 over 3 is 1/3. 5 over 1 is 5, and 5 over 3 is 5/3. And remember, each item has a plus or minus in front of it because we have 2 potential answers there. So now what we're going to do is test these possible zeros and try to find one where a remainder is 0, because that means it is a factor. And there's 2 ways you could do this. You could do synthetic division and figure out what gets you 0, or if it's quicker for you, you can do direct substitution. I'm going to go ahead and start by doing direct substitution, just because that can be a little bit quicker, but synthetic division will actually be really helpful in some cases as well. So if you want to do direct substitution, all you're going to do is pick a number from this list, plug them into your equation, and see which ones work. So I'm going to go ahead and start with -1. So f of -1 is going to get you 3 times -1 to the 4th minus 10 times -1 to the 3rd minus 24 times -1 squared minus 6 times -1 plus 5. Now the issue I have with people doing direct substitution is you have to be very careful when you're plugging in negatives. Anytime you take it to an even power, it's always going to become positive inside the parentheses. So this would be really like 3 times 1. This one's going to be -10 times -1, which becomes positive 10. -1 squared is 1, so this gets us -24 times 1. And then -6 times -1 is positive 6 plus 5. And now we can just go ahead and start simplifying. So I'm just going to be adding and subtracting where necessary. And we do get that when you plug in -1, you get 0. So this one I just got lucky. It happened to work. And you could start with any number. It doesn't have to be -1. You could pick +1, positive 1/3, -1/3, whatever you feel like choosing to test first. That's going to be where you want to start. The goal is just to always make sure you end with your answer or your remainder getting 0. So right now we know that x equals -1 is a 0 of our function. That means it hits the graph at x equals 1. Okay, and then we could go ahead and test some other numbers. Now the goal I would say here is to try to get your equation down to something that can be factored. So sometimes this is where synthetic substitution is very handy. If I would have done direct substitution with these numbers, synthetic substitution, it would have looked like this. I'm using all of my coefficients. Again, this is just an alternative method, but I'm going to show you why this method is very useful. You could plug in -3 or -1 at the end, go through and do your synthetic substitution. This is going to give me -11, multiply, get +11, add, we get 5, and then -5 to get our remainder of 0. So notice it gets you the same thing, but the reason the synthetic division is helpful is because now I have an equation with a lower degree that's called the depressed polynomial, and I can use this equation now to do synthetic division or do my direct substitution, and it's going to be less exponents, less numbers to work with. And if you can get your equation down to something that is x squared, so for example I'm going to go ahead and write these numbers here in synthetic. Okay, so I'd have 3, -13, -11, and 5. Now if I test with these numbers and I can get it down to something x squared, then I can use quadratic formula or I can try to factor it on my own. So I'm going to go ahead and test, let's say we test +5. So bring down my 3, we get 15, which gets us 2, 5 times 2 is 10. That gets us -1, which gets us -5. So this one happened to work out as well. So that means x equals 5 is another one of our zeros. So that means it hits the x-axis at 5. But now the reason this was so beneficial was because now I've got these new numbers here that form a quadratic, 3x squared plus 2x minus 1. And that kind of leads us into step 3. When you get the smaller polynomial, you can find the remaining zeros without having to test, because now I can do quadratic formula or I could factor using some other method. So if I want to try to factor 3x squared plus 2x minus 1, I could use quadratic formula if I wasn't sure how to factor it, or this one does happen to factor into 3x and x, and then 1 and 1, and I make my signs positive and negative. So now I can go ahead and, because I know that it's completely factored correctly, I can set each of these equal to 0. And that will find me the other solutions, x equals 1/3, and again x equals -1. Okay, so getting it down to a quadratic makes it way easier in terms of factoring, but direct substitution works just as well. It just may take you a little bit longer to guess and check your numbers. Okay, so either method's fine. Let me know if you have questions on each approach. And the one thing I want to add to this is that if you notice, we got -1 twice. Okay, that's called a double root, so I'll go ahead and type that here. And a double root means it bounces at that number. So when you're graphing it, I would hit -1 and then bounce off of -1 rather than going through it. So that's a special kind of root when you get that same number twice. Okay. If you have any questions about how to do either of the methods I showed, let me know in class. But that's it for today.